Hey everyone, today we're going to crack the code on a problem that trips up a lot of people in technical interviews, combination sum 2. We're going to pull it apart piece by piece, find that really elegant solution, and along the way, you'll pick up a super powerful technique you can use for a whole bunch of other problems.
So here's our game plan. First, we'll get a solid handle on the challenge itself. Then, we'll look at the first thing that might come to mind, a simple solution that, well, is a bit slow. After that, we'll level up and build a much smarter recursive approach, and finally, I'll reveal the secret trick that makes it all so fast and efficient.
All right, first things first, the challenge. What is this problem actually asking us to do?
At a glance, it seems simple enough, right? Just find groups of numbers that add up to a target. But the devil's in the details, and the real difficulty comes from two very specific rules.
Okay, so this is the heart of it. First, you can only use each number once in any given combination. But the second rule is the real kicker. No duplicate combinations in the final answer. So if you find the combo 1, 2, 5, that's it. You can't also have 5, 2, 1. It's the same combination. We only want each unique set of numbers one time. That's what makes this tricky.
Okay, so now that we know the rules of the game, let's talk about the first solution that often comes to mind. It's straightforward. It works, but as we're about to see, it comes with a hidden performance cost.
You know, this method is kind of borrowed from its easier cousin, combination sum I. The logic is pretty direct. Just generate absolutely everything and then throw all the valid combinations into a hash set. Since a set can't have duplicates, it does the filtering for us. It's a clever idea for sure, but it's not the fastest way.
And here's why it's not the fastest. See that little log of size factor in the time complexity? That comes from the work the computer has to do every time it inserts a combination into the set. It's an extra step, an extra bit of overhead. And in an interview, seeing that log factor is a big hint that, hey, there's probably a smarter way to do this. Our goal is to get rid of that completely.
So let's get to that smarter way. This is the elegant solution. We're going to build a recursive function that is clever enough to avoid making duplicates in the first place.
And believe it or not, the magic all begins with one super simple action. Sort the input array. That's it. This is the cornerstone of the whole optimized strategy. By sorting the array, we force all the identical numbers to sit right next to each other. And as you'll see, that's exactly what we need to pull this off.
Now, the heart of this new approach is a sort of pick and backtrack dance. We're going to loop through our now sorted array. For each number, we'll decide to pick it, add it to our current combination, and then dive deeper with another recursive call. As soon as that entire path has been explored, we backtrack by removing that same number, which frees us up to continue the loop and try the next path.
So we're sorting the array, and we're doing this looping recursion thing, but how does that actually stop us from making duplicate combinations? This right here is the aha moment where the whole thing just clicks into place. This is the absolute key idea. Just think about it for a second. Let's say our sorted array has 1, 1, 2. If we start a combination path with the first 1, we're going to explore every single possibility that begins with a 1. So there's absolutely no point in later starting a totally new, separate search that begins with the second 1, right? It would just create the exact same combinations all over again.
And this one little line of code is the entire secret sauce. Let's break it down. The I index part is crucial. It just makes sure we don't accidentally skip the very first element we're considering in our loop. But for every element after that, we check. Is this number the same as the one right before it? If the answer is yes, we just continue. We skip it. This move intelligently cuts off entire branches of our search, guaranteeing we only generate unique combinations from the get-go.
And that's really the big takeaway. By being smart during the generation process, instead of cleaning up a mess afterwards, we completely eliminate the need for that extra set data structure. We've built a cleaner, faster, and way more efficient algorithm.
And when you look at them side by side, it's crystal clear. The optimized approach just neatly slices off that pesky log of size factor. This is a fundamental shift in thinking, from generate everything and then filter to intelligently construct. And that deeper level of understanding is exactly what interviewers love to see.
So, as we wrap this up, I want to leave you with a question to chew on. This sort and skip trick, it's not just a one-trick pony for this single problem. It's a powerful pattern, a tool you can add to your coding toolkit. It's incredibly useful for a whole family of problems involving subsets, combinations, or permutations where you have to deal with duplicates. So start thinking, where else could you use this to write some really clean, really fast code?